So we have Scott Hawley, who is a professor at Belmont University, he's teaching physics there, physics classes to audio engineering majors. He's active in the Audio Engineering Society and the Acoustical Society of America. And Scott is contributing there to projects that combine ML, acoustics, and signal processing. So that sounds really, really interesting. Thanks, Scott, for joining us tonight. And your talk tonight is called Vibrary, Train Your Own AI Audio Classifier. And that sounds really, really interesting. So let's jump into that. Hello, Scott.
Hey, everybody. Timur and Josh, great to be here. Really enjoyed what y'all have been doing for a while. And I say go ahead and play the pre-recorded talk, and then I'll be happy to add some more stuff at the end. So it's about a 20-minute video I made.
Great. Here we go.
Hi, I'm Scott Hawley. I'm going to be talking about Vibrary, Train Your Own AI Audio Classifier. And this is work done with Jason Bagley, who's the main programmer on this, along with Brett Porter and Daisy Trainum. And Jason, Brett, and Daisy are all at Art+Logic. The GitHub repository for this project is here, and you'll see that posted repeatedly throughout the talk. So the basic idea is that producers and composers often have very large libraries of audio samples and clips, and usually these have some kind of metadata tags to tell you what the clip is about, but they don't always agree. And so sometimes it could be a challenge to find what you want. And so one idea is to allow people to train their own machine learning system to tell it what sorts of things they're looking for. Train your own. We really do mean the end user. So a lot of machine learning systems these days are trained by a company and then deployed to the end user, and the end user can only use the trained model, but they can't train it themselves. As far as audio tagging goes, or audio classification, National Instruments has their sounds.com. There's some apps called EXO, Atlas, Samply, and probably others to help you find samples on your hard drive. But as far as we know, none of them allow the end user to train their own model. And so we're about trying to democratize AI and machine learning by putting training in the hands of the end users. But end users tend to lack the computational resources, which usually involves graphics processing units. Tools that are trainable may only be accessible through a Unix command line. There's not some nice user-friendly way of doing it. Also, it's the case that end users are not data scientists, and that can actually affect the results you get. We'll say more about that later. The basic idea with Vibrary is we combine the GPU server to get computation to people who may not have the hardware with a user-friendly GUI client on the front end. So a quick summary of the project is there's nothing new under the hood. This idea of using convolutional neural networks on spectrograms, and specifically MEL spectrograms, has been around for quite a while, and our model is actually rather simplistic. But the package of putting it together in a way that makes it easy for end users without specialized hardware or expertise to be able to do this, that's the main effort here. Our method is fast and accurate. We find that it tends to be more a function of the user's choice when they make their own data set than it is about the particular neural network model system that we're using. A little bit of the timeline on this. I have a club in Nashville called Aspire, which is people who are into audio or acoustics research and development kind of getting together to pool our efforts or share what we're working on. And in the context of this, I was having coffee with Ethan Henley, who is a producer, and he expressed this issue of, gosh, I've got so many audio samples. How am I going to find what I want? And I said, well, actually, I have a audio classifier. It's one of the first projects that I did when I was first learning about machine learning. My system, I called it Penati, just based off these supposedly ancient people that had really big ears that could hear really well. And so throughout this talk, you're going to hear me talk about client and server. The client is the Vibrary GUI. The server is the neural network classifier training system, which by default is Penati, although you could replace it with something else. So really Vibrary ends up being kind of a sweet front end for Penati. It wasn't really going to turn into a real product. That was just too much effort. But right at that time, Art+Logic announced a contest where they said, send in your idea for a audio related app and we'll pick one and turn it into a real thing. And so I submitted my prototype, which back then wasn't called Vibrary, it was called Sorting Hat. And the HAT stood for Hosted Audio Tagger. And the prototype was built through a hackathon. And so that got picked by Art+Logic. So we've been working together for a few years now. Okay, so here it is. This is Vibrary. I'll show you a demo in a minute. And so the client server system, the client is the GUI. It's built in JUCE with C++. And the server, which gets connected to just over SSH. We don't have any special API yet. You could write one if you want. Right, so we just SSH the data back and forth. Now, ideally, the server would be, say, up on Amazon, and it would spin up when you need it and spin back down. We haven't gotten to that part yet. So right now it is supply your own server, essentially any computer that allows SSH access where you can install Python and Keras and TensorFlow and stuff. And as long as you can SSH in there, then you're done. And there are instructions on doing this. Jason has written up a lot of great instructions on the GitHub site. So I'll say more about that later. A little bit of background on the method, right? Audio classification, it's a subset of music information retrieval, which is a really, really big field. People have devoted their lives to it. I am not an expert in that area. This was just a project I wanted to try, but usually you extract features from the audio in various ways. You might use it for a recommendation system like Pandora. One way of doing this is by turning the audio into an image by making a spectrogram and then use image classification methods. This has been done for quite a while. I noticed it. Kyung-Wee Choi, who's at Spotify now, he won the best paper at the Music Information Retrieval Society a couple years ago, and I kind of dumbed down what his work was so I could make it work. All right, so one idea is don't actually upload the audio to the server in the cloud. Instead, generate the spectrograms locally using the user's CPU and then upload them and train on the cloud. So the basic workflow goes, you, the user, build the data set. The client will generate the spectrograms. It'll upload those spectrograms, train the neural network, and then you'll download. Essentially, you'll download a copy of the neural network. You'll download the weights that make up the neural network. And then the Vibrary client will execute a copy of that neural network in what we call inference mode. Nice things about doing this, the spectrograms are a lot smaller than the audio itself. The original prototype, we were uploading raw audio, and that just takes way too long. Also, if you upload raw audio, then you could get in trouble for licensing, for redistributing, say, copyrighted material. So if you're only uploading the spectrograms, then there's a huge data reduction, and you're not going to reconstruct the full quality audio from the spectrograms. And then one other thing about this approach is that by using the MEL spectrograms, we're taking advantage of some domain knowledge of audio. We're not just training a raw waveform domain neural network model like, say, WaveNet. And that actually allows us to perform pretty good on relatively small data sets. Small meaning like tens to hundreds of examples, as opposed to like tens of thousands or millions. In order to get this thing working, we try to keep it simple as far as what we imagined producers and composers would want. It is open source, so if it doesn't have features listed that you want, you can add them. One thing is that it's modular, so you can keep the client, swap out the server network. One simplification is that for each set of neural network weights, which we call a sort file, we only associate one tag or one category per audio clip. You can do multiple different sort files, but you're only going to get one tag per sort file per audio clip. That's just to keep it simple, right? It also doesn't do hierarchies, but we allow for multiple different sort files. So you could say have a sort file for genres and another one for instruments or whatever, and you could run them in succession. And people could share their sort files with one another. You know, there are companies that will sell famous producers presets to, say, a mastering plugin or something like that. So you could imagine people sharing their own individual sort files that they've worked on. We don't have an infrastructure for that, but you know, Dropbox or Google Drive, that would work. Also, we're not going to hang on to people's spectrograms. We could, but also defaults, we just stick to mono, sound clips of 3 seconds and 44.1 kilohertz. The idea is what's likely to work for most people. These defaults can be changed. And then people may want to know, well, how many audio examples should I supply for training? And the answer is, well, it depends. So I did some tests. My friend Kyle is a composer, Kyle Baker, and he provided me with a data set of 9 different instruments that he had. There's a rather well-known genre database called GTZan, and Fraunhofer IDMT has a data set of guitar effects. What I did was I plotted sort of the accuracy of the model versus how many examples you supply per class. And what you see is, right, the more examples, the more accurate it is. Some of this is a bit artificial in that there are 9 instruments, 10 genres, 12 effects. So it's not necessarily that effects are necessarily harder than instruments, but that's an example. A different neural network model might have different properties. For example, like a one-shot learning model, you could install one of those and see how that works out. But the training is fast, okay? So somewhere on the order of tens of seconds to, say, less than a couple minutes, even for relatively large data sets. It just goes pretty fast. I'll now show you a demo of Vibrary. So I'll go to github.com/artandlogic/Vibrary, go to releases, and I'll download the release. Just make sure I don't have it already. Yeah, I'll grab a new version. And so I've downloaded that, and we'll unzip it. And there's our app. So we'll run it, and we'll probably get an error from the OS because it doesn't know what it is. So then we can go to System Preferences, Security and Privacy, and press Open Anyway. And then let's double check on that. Okay, sometimes this happens with macOS Catalina, depending on how it was compiled. Yeah, I've noticed this with some other apps as well. Yeah, so another thing that we can do is go into Downloads, Vibrary.app, Contents, macOS, and just run it directly. There we go. And it's telling us that our Vibrary is empty, meaning that we haven't actually categorized any files. It says choose a sort file, and we've got a couple different sort files that have come with it. These are pre-trained neural network weights. If we press the space bar here, we can see one of them is pre-trained with brass and drums and percussive sounds and soundscapes. The other one is just trained on different parts of a drum set. So let's do that. I'm going to grab some audio from a different data set. This was not trained on. So yeah, so we'll grab some kicks and we'll see if it knows that they're kicks. So it generates spectrograms, and look, it knows they're kicks. Okay, and similarly, we can do some toms, and just in the interest of brevity, again, these are totally new files that this system wasn't trained on. What else can we do? Okay, cymbals and snares tend to be interesting because sometimes the snares or the cymbals can have some effects on them, and it's not uncommon for models to get them mixed up. Yeah, so occasionally, even though it says snare, it thinks it's a cymbal. So that's an example of inference, right, with different types of tags. Again, I can press spacebar there. Now, what about training? Oh, one other thing I might mention is that you don't have to do individual files. You could drag in entire directories. So for example, okay, this is, I'm gonna have to speed this up in the video. I can drag an entire directory of symbols in here. This is gonna take a little while. So it's generating spectrograms for all of those. And you can see this little bar is getting shorter. It'd be nice if we parallelize this so it would go even faster. So I'm going to speed this up. Another thing we can do is we can listen to each of these. I'm not sure if my audio, yeah, you might not be hearing that, but you can hear it, or you can press the space bar. And from Vibrary, you can drag these files into different bits of DAW software as well. Oh, that's interesting. I've never tried that before. Okay, now if we choose a different sort file, then it doesn't have that. It says here Vibrary is empty for that particular sort file because we could have used a different categorization scheme. So what I'm going to do now is train a network. So it says create new sort file, and to connect to the server, so we need a username and a server. In my case, the server is called Hinton. And this is something that you need to have SSH access to and set up key exchange for this. So it's not going to get prompted for a password. And then we can go up here to our train. It says create tags. So we're going to create some tags, and we can either type in a name or we can drag in a directory. So for example, I can drag in like this acoustic guitar stuff. And then I can drag in, say, some keyboards and sound effects. And I'll just do the other two here. Oops. Strings and voice. All right. And then when we're ready, we can say train your Vibrary. And we'll say June 9 demo. And then it's going to generate spectrograms for all of those. And if you're running from the command line, you actually can see an entire log of everything that's going to happen. And we have a little status bar that's going. When it's finished generating all the spectrograms, it's going to upload them to the server. So now it's uploading. And it tries a few different SSH protocols first. And so once that's uploaded, then it's going to train the neural network. And this looks a lot nicer if you run it locally, but this is the training. And it'll be done. It's now done. And we're going to download the neural network weights. And it says we're done. Okay, that's for the old sort file. Here's June 9 demo. And so now we can take some other data and drag it in, see how we do. Okay, and it thinks they're mostly acoustic guitar, but some of them are getting classified as something else. Sometimes if you listen to these, yeah, it's not 100% accurate. I could have added some more examples. Let's try the keys. Oh, I didn't want to do that. Drag in the keys. And it thinks they're mostly keys, but some of them are sound effects. There may be some overlap as far as what's in the sound effect list. Sound effect is kind of a grab bag of a bunch of different things that I just pulled in from Apple Loops. Okay, thinks those are all sound effects. And for example, strings. So we can also, whoops, we can drag in individual groups of files. We can drag in individual files like that. So those are supposed to be strings, but it's thinking some of them are keys. And then we've got voice. Drag those in as well. And yeah. All right. So it seems to think a lot of those are strings. Interesting. That's not strings. Well, so work in progress. That's the basic idea. And so you can create your own sort file there. Demo for Vibrary. If you want to train using your own server, you can come in here and change that information. And we've got information on the Vibrary GitHub page for setting things up. Jason has written a lot of good documentation for if you want to build, if you want to set up the server. Got it over here. And I'm actually working on a version that's updated to TensorFlow 2.0. So hopefully that'll be ready very shortly. That's it for now. Thanks. So extending Vibrary beyond what we imagined for it, as far as users, well, we really haven't had a chance to really put this thing through its paces as far as what it's good for and what it's not. There are lots of different studies in the MIR literature for people detecting things like beats per minute and keys of songs and things. We just haven't tried it, so we're really curious to see what people do with it. And certainly training models and sharing them with others would be neat. Tips for improving the user interface. Love to hear about that. As far as developers, so this is built in JUCE, And so many of you are already familiar with JUCE through Josh's teaching. There are all kinds of different improvements that could be made to the Vibrary client. Some of the plugins I mentioned at the beginning of the talk have a really nice display where they sort of colored dots for the different categories. And yeah, we don't do that. It'd be nice to be able to do that. Also, file formats like contact, we don't do those. Getting some help with unit testing would be great, right? And this thing only works for Mac. Also, I should mention Art+Logic. They hire audio developers from time to time, and everybody works remotely. It's a complete work remotely company. So just a little plug for them. As far as machine learning researchers, well, you could use Vibrary as a front end and then swap out the server model with your own. For example, Dirty Ponds, and over in Barcelona, there's this great thing called, it's pronounced Musician, and it's also based on TensorFlow. And so if you wanted to swap this out, I haven't really written out the full documentation for doing it, but the basic thing that happens is Vibrary is going to make a bunch of spectrograms. It's going to save NumPy, compressed NumPy versions of those files. It's going to send a gzip tar file of that to the server. And the idea is each folder in a directory is where all the classes are. That's a pretty standard way of organizing things. And then we train the model. That just involves executing some command via SSH. And then we download a protobuffer file from TensorFlow. And then Vibrary uses that. So if your machine learning model can simply take in a bunch of spectrograms, then do its training, then produce a protobuffer file that we can download and execute, that's all that really needs to happen. Now, one other thing that'd be great for some developer to try is maybe we don't even need the GPU server. Maybe if we do some data reduction on the front end with, say, principal component analysis, maybe people could do this on their CPU. It's not a maybe. We know people could. We just haven't gotten around to writing it. So, summary of the project. Letting users train their own models is, I think, one of the most exciting things about machine learning. And as far as I know, there's an app called Runway ML. It's great for visual art, and you can try out all kinds of different image processing algorithms that people have trained, and they allow GPU cloud credits. So for Vibrary, the underlying algorithm, it's not all that fancy, but what we're trying to do with it in terms of make it so ordinary people could use it, and not just producers or composers, but even, say, in my classes as a professor when I teach audio classes, this idea of classification is a neat thing that people are interested in, but it's not been accessible to them. So making it easier should be interesting. Once again, it's up on GitHub. You can mess with the source, swap things out, send us pull requests, send in issues, and we welcome any feedback. That's it. Thanks.
Right.
Yeah, thanks a lot, Scott.
Thank you so much, Scott. This was really, really quite impressive stuff. We have a few questions. First question is from Marvotronics. Are there Docker images for the server?
Sorry, I got out of sync between the YouTube stream on my end is about a minute behind the live Zoom. So I'm trying to find our where did the Zoom thing go?
Yeah, it's tricky to find it sometimes.
It's somehow it moved. I can't see anybody anymore.
Can you hear us?
I can hear you, and I'm just going to assume everything is fine.
Yeah, we can hear you. Everything's fine. So
okay, good. So I'll just go purely on audio alone.
We're speaking to you from the future.
Here, so.
Right. There's like this tiny, tiny little window up in the. Oh my gosh. Anyway, there's a tiny Josh. Excellent. Sorry, Timur, can you repeat the question, please?
Question was whether there are Docker images for the server.
I think Jason answered that. The answer is not right now. That would be something that would be really nice. The server is essentially, so it's this package Panati. So, and you can download that and install that just with pip. You can clone the repo, and it's really just a pip install Panati and it'll do itself. So as long as you've got some computer somewhere that you can SSH into, the setup should be fairly simple.
All right. Then we have a question from Akash asking, what kind of resolution do we need to, what kind of resolution do we see for the spectrograms as images when it's sent from the client to the server?
Yeah, there's a default value that we set that seems to work pretty well. I mean, they're pretty small. I don't remember the exact dimensions, but it's something like 100 by 150 or 170 or so. If you change the duration, so we set a default of 3 seconds for each spectrogram. If you change that and make it longer, then you'll get larger spectrograms. And currently that's not in the binary that you download, that's not in settings. It's kind of hard-coded, but it'd be really simple to expose some of those things to allow users to make more changes as far as what the options are for spectrogram resolution and things like that.
All right. Then the next question is, how many classes can you have?
Right. Yeah. So never tried a lot of classes. There's no hard-coded limit in the code at all. I would say advisably, so I think the last fully connected layer on the neural network has 128 elements to it. And I wouldn't recommend trying to go above 128, but you could. There are models that do this that train on, for example, 1,000 classes. And for our use case, we just didn't anticipate people trying to do that. So in the interest of speed and storage and so forth, we made a choice to keep it kind of small on that end.
All right. So
let me rephrase. There's no actual limit in the code anywhere. You can try whatever you want.
I think that clarifies it. Yeah.
Okay.
Thank you. There's another question from Akash who's asking, what's the average accuracy of the system, approximately based on the samples it's seen from now, which have been validated? And is there some way for the client to correct the tags?
Great question. Okay, so as I mentioned earlier, the accuracy depends a lot on you and the data set that you create. And so I'll just give you one example. A lot of sample libraries will have not just pure recordings, but they'll have kind of affected, noisy sorts of things. Like I've noticed a lot, there are things that get called a snare, where it's really this kind of noisy thing that might have a lot of sustained high frequency stuff. And that'll get classified as a symbol a lot of the times, because, and then you go back and listen to it and you're like, oh yeah, I could totally see why it thinks that's a symbol, because it's not a real snare, right? So some of these accuracy things are a bit subjective. But for example, all the data sets that I was using for things earlier today, it's not unusual to score, say, 90% accuracy on only, say, like 20 or 30 examples in a class. And you could set it to train for longer. So we also set a certain number of, we call it epochs or iterations as the machine learning model is training. And we set it for a default of 30, which, as you see, it goes through in less than a minute. If you wanted to train for longer, you could bump up the accuracy to a certain point, up to a limit. It depends on the data.
All right. So last question from Marvotronics. Do you get a confidence rating for a tag?
Yeah, that would be a really nice thing for us to do. So far, we don't do that. And the information physically exists in the computer. It is essentially computed as part of the classification algorithm. We just kind of have thrown that information out once the classification is made. I'm not sure the best way to show that in the user interface. So it is possible. And if someone wanted to go in and modify the JUCE code to accommodate that, then that'd be great.
All right. So there's one more question just now from Toby. Mm-hmm. So Toby's asking whether you have experimented with synthesizing samples based on models like GAN.
Okay, that's a completely different application. So this is not a generative model. This is just a classifier model. So it only takes existing inputs. There are some really great work with generative adversarial networks and audio, in particular, like the Google Magenta group. They do some really great work with that. Mm-hmm. Chris Donahue is a guy who does some neat work with that. But yeah, that's not what this project is about.
Yeah.
All right. Yeah, thanks. Thanks again very much, Scott, for answering all these questions and for your wonderful presentation.
Mm-hmm. So, sure. Can I make one other comment since we're here? Since this is all about learning audio programming and so forth, and you have in my bio, I helped curate a web page of sort of advice for students, for people who are interested in getting into machine learning and audio, or deep learning and audio. and it's on GitHub, but it's a page that's full of like links to online courses and books and things like that. And so if one of us can post that into the chat, I can post that in the chat window in just a minute, and people who are interested in learning more about it can find some of those resources.
Yeah, I'll post it in the video description as well.
Cool.
So, and just one note on that. On that note, for a primer, if you've never done any sort of machine learning and you're looking to just get your feet wet with it, a great course to start off with would probably be Rebecca Fiebrink's course on Cadenza, which is a creative machine learning course, and it is fantastic. It's a course that I took while I was a student at Goldsmiths, and she's one of the authorities on this field. And that's a great one where she provides a very high level overview without getting too crazy into the math. And it's fantastic. I highly recommend it.